तेरा रहे माँ रंग बिरंगा ऊंचा।
हेलो सर, स्टार्ट करें। Nothing great will ever be achieved without great men, and men are only great if they are determined to do so. A very good morning to all the dignitaries, guests, delegates, HOD of various departments, faculty member, and dear students. With joy and immense pleasure, on behalf of Institute and Science and Laboratory, ISR IPS Academy, I, Dr. Reina Jadhav, feel privileged to extend my warm welcome to all present here to celebrate DAE Iconic Week for the celebration of Azadi Ka Amrit Mahotsav to commemorate 75th year of independence of India. On this occasion, Institute of Science and Research, IPS Academy, is organizing a Vyakhan Mala and scientific interactive session in this regard in collaboration with Department of Atomic Energy, DAE, Mumbai, Maharashtra, and Raja Raman Center of Advanced Technology, Indore. Department of Atomic Energy is a department of central government with headquarters in Mumbai, Maharashtra. DAE was established in 1954. DAE has been engaged in the development of nuclear power technology, in the field of agriculture, medicine, industry, and basic research. DAE is comprised of 5 research centers, 3 industrial organizations, 5 public sector, and 3 service organizations. BARC, RRCAT, NPCL are all being managed, all these institutes are being governed by DAE. And IPS Academy is one of the premium institute of Central India. The academy with 16 colleges, 75 courses, more than 10,000 plus students, boasts of a unique marvelous infrastructure spread over 60-acre lush green campus. So basically IPS aim to be one of the premium institute of the country, dedicate to create, applicate, disseminate of knowledge, skill, spirit of competition, competitive excellence, building up generation of global citizens and value drive professionals to the corporate world and the society. So as a guest for today's event, we have among us Dr. Pankaj Mishra, Scientific Officer, RRCAT Indore, Shri Govind Panchali ji, Head CSD Chief Engineer, RRCAT, and Ms. Gitanjali as a Scientific Officer from RRCAT. So, we welcome you all, sir, in IPS Academy. Darkness cannot be wiped out by blackness. Only a bright light can accomplish it. In the same way, let us hope that the light of the education move us towards growth, liberty, and equality. So, we will have a traditional auspicious lamp lighting ceremony as a tribute to Ma Saraswati, goddess of knowledge and prayer, to shower her blessings on us. So, I would like to request all dignitaries, guests, Dr. Pradeep Joshi sir, Dr. Jiten Tripathi sir, Mrs. Ruchi Srivastav, and Dr. Dipali Shukla ma'am to please join us on the stage for the lighting of lamp in front of Ma Saraswati. Sir, please. Ma'am, please add this on.
शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ।
हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ। हे शारदे
तू स्वर की देवी, ये संगीत तुझसे, हर शब्द तेरा, हर गीत तुझसे।
तू स्वर की देवी, संगीत तुझसे, हर शब्द तेरा, हर गीत तुझसे।
हम हैं अकेले, हम हैं अधूरे, तेरी शरण में हमें प्यार दे माँ।
हम हैं अकेले, हम हैं अधूरे, तेरी शरण में हमें।
Thank you very much, all of you. Now, moving with the program, I request Dr. Pradeep Joshi, sir, HOD Department of Mathematics, to present a floral welcome to Honorable Guest Dr. Pradeep Mishra, Senior Scientist, Department of Atomic Energy, RR KET. Now I request Dr. Jitendra Pathi, Head, Department of Physics, ISR IPS Academy, to present floral welcome to Shri Govind Panchali, H, Head, CSD Chief Engineer, RR KET. Thank you, sir. Now I request Mrs. Ruchi Srivastav, Head Department of Chemistry, ISR IPS Academy, to present floral welcome to Ms. Gitanjali as a Scientific Officer at RR KET. Thank you, ma'am. I welcome all the dignitaries, guests in ISR IPS Academy and feel privileged to have you all here. Thank you very much. Now, on moving with the program, we have among us Dr. Pankaj Mishra, is a senior scientist and head Oxide Nanoelectronic Lab at Raja Raman Center of Advanced Technology, Indore. He is also Associate Professor of Physics Science at Homi Bhabha Institute, HBNI, Mumbai. He joined RR KET in 1998. He obtained MSc in Physics from University of Lucknow in 1996, MTech in Material Science from Indian Institute of Technology, Kanpur in 1998, and PhD in Semiconductor Physics from DAVV in Indore 2008. His current research interests and activities include growth of thin film, quantum structures, and multi-layer device structure of metallic oxide semiconductors and high-K dielectric oxide using pulse laser deposition and atomic layer deposition technique for UV and non-volatile memories. He has published more than 150 research articles in international journal and contributed 4 books chapter. So we welcome you, sir, and request you to please deliver a talk among us. Sir, please.
पॉइंटर है क्या? A very good morning to all of you, students, faculties of IPS Academy. As you might be knowing, Azadi Ka Amrit Mahotsav is an initiative of Government of India to celebrate and commemorate 75 years of independence and glorious history of its people, culture and achievements. Raja Ramanna Center for Advanced Technology, which is a premium research institute of Department of Atomic Energy, is also celebrating Azadi Ka Amrit Mahotsav. In this series, we are organizing a series of lectures at various universities by senior scientists of RRCAT to showcase the contributions of Department of Atomic Energy and Raja Ramanna Center for Advanced Technology, Indore, in nation building. We'll also discuss the career opportunities at Department of Atomic Energy at various levels. So, next slide please. So, as you know, Department of Atomic Energy was established on August 3, 1954, and Dr. Homi Jahangir Bhabha, who was the father of Indian nuclear program, was the founder director of atomic energy establishments. Since its inception, the Department of Atomic Energy is engaged in the development of nuclear power technology, applications of radiation technology in the field of medicine, agriculture, and basic research. So in general, DAE comprises of 5 research centers, out of which one is Raja Ramanna Center for Advanced Technology, Indore, Bhabha Atomic Research Center in Mumbai, and Indira Gandhi IGCAR at Kalpakkam. Similarly, 3 industrial organizations, 5 public sector undertaking. I'll show the organizational chart. Then 3 service organizations, 2 boards, BRNS and NBHM, for promoting and funding the extramural research in nuclear and allied fields and mathematics. And then Homi Bhabha National Institute, which is a deemed university and institute of national importance. And then we have a Atomic Energy Education Society that provides educational for children of DAE and employees. Yeah, next slide. So this shows the flow chart, Department of Atomic Energy, and then there is the Atomic Energy Regulatory Board, and it has 5 R&D centers, as I mentioned: Bhabha Atomic Research Center, Mumbai, then Indira Gandhi Center for Atomic Research, Kalpakkam, Raja Ramanna Center for Advanced Technology, Indore, and then Variable Energy Cyclotron Center, Kolkata, and Atomic Minerals Division at Hyderabad. These are the R&D centers. Then there are 5 public sectors undertaking: Nuclear Power Corporation, Mumbai, and then Indian Rare Earths Limited, Mumbai, Uranium Corporation of India, Jadugoda, Electronic Corporation of India, ECIL, Hyderabad, and Bharatiya Nabikiya Vidyut Nigam Limited, Kalpakkam. There are 3 industrial organizations: Heavy Water Board, Mumbai, Nuclear Fuel Complex, Hyderabad, and BRIT, that is Board of Radiation and Isotope Technology, Mumbai. And then 3 service organizations are Directorate of Purchase and Stores, Directorate of Construction Services and State Management, and then General Services Organization, Kalpakkam. So we have 8 added institutes Tata Institute of Fundamental Research, Mumbai, Tata Memorial Cancer Center, Mumbai, and Saha Institute of Nuclear Physics, Kolkata, IOP, Bhubaneswar, Institute of Plasma Research, Ahmedabad, then Harish Chandra Research Institute, Allahabad, Institute of Mathematical Sciences, Chennai, and Atomic Energy Education Society, Mumbai. So you can see the atomic energy establishments, almost all part of the country we have atomic energy establishments. You can see BRC, then RRCAT in Indore. Pointer is there? Hua kya? Okay. So these are the mandates and deliverables of Department of Atomic Energy. So the mandate is research, development, demonstration and delivery of nuclear power by research on reactors and fuel cycles. Then radioisotopes, their productions and applications in medicines, agriculture and various fields. And then of course national security and advanced technologies in the area of lasers, accelerators, supercomputers, which aid to the nuclear programs of the department, and then direct research in all science and engineering disciplines to cater the requirement of department. So let us discuss the scenario of nuclear power in the country. So if we look at the modest lifestyle of people in country, we need about 3,400 terawatt hour per year of power, and realistic evaluation is that all sources, including nuclear and all conventional sources, we produce around 1,230 terawatt hour per year. So there is a shortfall of around 2,100 terawatt hour per year. So there is a huge scope for the higher growth of nuclear energy to fulfill this requirement of additional power. So presently if we see around 86% of our electricity needs are met by burning the coal, oil, fossil fuels, etc. However, as we know that burning of these fossil fuels is hazardous to environment, and there are many restrictions, and we are moving towards zero emission policy. So we have to get rid of these conventional energy sources. So the role of nuclear energy becomes very important in that scenario as far as environmental pollution is concerned. So let us compare the electricity generated and the kind of infrastructure required by different means of electricity generation. So let us take an example of hydel power plant. So around 1,000 megawatt hydel power plant requires a huge infrastructure and submergence area of around 2,000 to 5,000 hectares. And compared to that, if we see the 1,000 megawatt coal fire plant, so the land requirement is around 70 hectares, much smaller than in case of hydel plants. However, the requirement of coal is around 38,000 tons per year, which turns out to be 5 train loads of 2,000 tons per day. And as I mentioned, there is a emission of hazardous gases like carbon dioxide, sulfur dioxide and NOx. Quantities are roughly given in tons per year. So they are huge emission, and then of course ash generation. So compared to these two electricity generation sources, if we see the 1,000 megawatt nuclear power plant, so land requirement, if you see, it's reduced to 20 hectares. So we need much smaller land for establishing a nuclear power plant. And fuel requirement, you compare with the conventional coal plant, it is around 120 ton per year, so much smaller than the coal-fired plant, and emission is negligible. Waste is also hundreds of thousands of times less. So, considering all these things, the nuclear energy has a bright future and should be utilized to meet the electricity requirement of nation. So, let us see what consists of this nuclear energy process. So, it consists of a fusion reaction. Most of us know. It is a reaction in which the excited compound undergoes through fission process, and by absorption of high energy neutron, it fragments into parts, and in the process it generates the fast neutron and protons and gamma radiation and different types of nuclear radiations. So these energy generated in this process is utilized for generation of electricity. So comparing the two energy sources, coal-based and nuclear energy, so it is 1 megawatt per day energy requires, in case of coal plant, around 3 tons of coal, while in case of nuclear plant, it is 1 gram of uranium 235. So, Indian nuclear power program, as you know, that India has a 3-stage nuclear power program, and it was formalized by Dr. Bhabha, and that is actually based on the generation of energy utilizing the thorium, which is having huge reserve in our country. So, to give an estimate, the uranium reserve in the country is around 61,000 tons, which is around 1% of the global uranium reserve. But at the same time, we have 225,000 tons of thorium reserve through mangite sands in coastal areas, and that consists of around 25% of global thorium reserve. So we are rich in thorium, and that's why we as a nation need a program where we should be utilizing thorium as a source of energy rather than uranium. So Dr. Bhabha very meticulously has adopted a 3-stage energy program for the country, in which the stage 1 consists of pressurized heavy water reactors, which use natural uranium as a source, and in the process it generates power as well as plutonium as a byproduct. This plutonium is again a fissile material, and it can be used in the second stage as a fuel material, and these advanced reactors are called fast breeder reactors. See, as the name suggests, fast breeder reactors, this is actually used to breed the thorium. The point is that, as I mentioned, thorium is not a fissile material, and therefore it is not useful for the energy applications because it doesn't go the fission process. So its breeding is required before it can be used, and it can be done by bombarding it with high energy neutrons and proton, which converts into uranium 235, and that can be used as a source of energy. So these fast breeder reactor uses the plutonium and uranium as a source, where plutonium is the fission material, and that converts further these uraniums into plutonium. And once we have a sufficient plutonium reserve, we can introduce thorium as a blanket in the stage 2 reactors, which will convert thorium into uranium 233, and in stage 3 we should be having self-sustaining nuclear reactors based on thorium 232 and uranium 233. Here uranium 233 is acting as a fissile material, and it is generating energy, at the same time it is converting thorium-232 into uranium-233 through mutation process. So what country is doing? So this is the scenario. As I mentioned that since we have a 3-stage nuclear program, and the stage 1 is to develop these pressurized heavy water reactors because they are used to generate plutonium. So presently we have 22 reactors with a total capacity of 6,780 megawatt in operation, and one reactor at Kakrapara KAPP3, which is 700 megawatt pressurized heavy water reactor, is connected to the national grid on January 2021. In addition, there are 8 reactors totaling to 6,000 megawatt. They are under construction at various stages, and the government of India has given approval for construction of 12 more nuclear power reactors, out of which 10 will be indigenously developed pressurized heavy water reactors, and 2 will be light water reactors, and that will be developed in collaboration with Russian Federation. So it is expected that on progressive completion of the project under construction and accord sanction, the nuclear capacity will reach around 22,500 megawatt by 2030, which is very important to meet the electricity requirement of nation. So R&D institutes of DI, they are involved in the research and engineering development in civil, electrical, electronics, computers, mechanical, cryogenics, material science, robotics, etc., to meet various requirements of nuclear energy generation, and then design, development, engineering and operation of research reactors, fuel fabrication, reprocessing and waste management, which is a very important part of nuclear power generation, and then radioisotope generation, their application in medicine, agriculture and industry, and research and development in frontline areas of sciences and engineering to develop various technologies and devices required for societal applications as well as departmental needs. So I'll discuss some societal and industrial applications. At this point, I'm not going into much detail of nuclear power plants and how they are working. Rather, we'll discuss some of the technologies which have been used, developed by Department of Atomic Energy, and they are being used for societal and industrial applications. So first is the sewage sludge hygienation research irradiator. As we know that huge amount of sewage sludge is generated every day in our country or anywhere, and this sludge is actually infectious and contains variety of bacteria, but at the same time they have huge amount of micro and macronutrients which can be used for enhancing the crop production. So what is done is the hygienation of these sewage sludge by using the gamma irradiation. So a cobalt-60 source based gamma irradiation facility has been developed for the hygienation of these sewage sludge, and then they can be converted into useful manures and can be used for improving the quality of soil and crop. And this shows the sewage irradiation plant at Gajrabadi, Vadodara. This was the first plant developed in Ahmedabad, with the help of Ahmedabad Municipal Corporation. And then the right hand side figure shows the Nisarguna plant, which is actually a biogas generation plant. It uses the biodegradable waste such as waste from kitchen, the green and dry leaves, the grass and paper, in fact gobar, etc. They can be used in this plant to generate the methane gas, which can be used as a fuel for domestic application, as well as manure, a very high quality manure. So this shows the Nisarguna plant developed at Symbiosis Pune campus with the help of Department of Atomic Energy. So radiation processing of food commodities is a very important area. Generally these food commodities often contains bacteria and they are cause of the food poisoning, and they can be troublesome for the health. So radiation processing is one such techniques which can be used to get rid of this. One example is E. coli virus, which is found in the fresh meat, and how dangerous it is we all know, and that can be prevented by using the radiation processing. And normally 8 to 10 kilogray of gamma radiation or 10 mega electron volt of electron radiation is used for processing of food commodities, and it helps first of all to hygienize the food commodities, and at the same time it delays the sprouting in some of the items such as potatoes and onions, so enhance their storage life. So various gamma irradiation facilities developed by Department of Atomic Energy in the country are listed here. So one is Food Irradiation and Processing Lab at BRC itself, and then at various locations in Nasik, Mumbai, Ahmednagar, etc. So there are 15 such gamma irradiation facilities in India developed by Department of Atomic Energy. And radiation induced mutation and cross breeding is also used to develop good quality crop varieties, and various crop varieties have been developed through this process, and around 49 crop varieties are available for commercial cultivation. And these seeds, they show the improved characteristic in the form of higher yield and earliness in the crop product, and then large seed size, etc. So the crop varieties includes groundnut, the bean of urad and tur, and then black and green grams, soya bean, sunflower and chavli, etc. So there are 14 crop varieties. They are radiation induced mutated to result in the better crop production. So these are the images of popular Trombe groundnut varieties which have been made available at different part of countries for commercial use. And this shows the indigenously developed teletherapy machine named as Bhabhatron 2 for treatment of cancer, and it consists cobalt 60 isotope as a source for gamma radiation, and in a very controlled way these gamma radiations are dosed to the patient for the treatment of cancer. And this machine Bhabhatron 2 has been installed at many places in the country. 12 channel tele-ECG, which is a very compact model, and results can be seen on the mobile itself through an application, has been developed for cardiac monitoring. It records 12 ECG channels simultaneously, and as I mentioned, report can be directly sent to the mobile, so it is a very compact and easy to use ECG system developed by DAE for medical use. And then Board of Radiation and Isotope Technology is involved in the production of various kind of isotopes used for healthcare, industry, agriculture and research. So whatever isotope we see for irradiation of either food grains or medical equipments or irradiation purposes, all these isotopes are developed by Board of Research and Isotope Technology, BRIT, Mumbai. The water purification is another area where Department of Atomic Energy has contributed, and a water purification system, depending upon the requirement of that particular region, have been developed to remove the toxic and contaminants such as arsenic, iron, fluorine, etc. And also desalination plants for converting seawater into the potable water have been developed by removing the salinity using the membrane process. And this image shows the 4.5 MLD multi-stage flash plant at nuclear desalination demonstration plant Kalpakkam, coupled with the Madras Atomic Power Station. And now coming to societal contributions of Raja Ramanna Center for Advanced Technology. As you know, it is a premium research institute of Department of Atomic Energy engaged in the non-nuclear frontline research areas of lasers, accelerators and various advanced technologies. You can see the beautiful picturesque campus of RRCAT. So the foundation stone of RRCAT was laid down on February 19, 1984 by then President Gyani Jail Singh. The top image shows that occasion. And in 2005, the center was renamed from Center for Advanced Technology to Raja Ramanna Center for Advanced Technology by then Prime Minister Dr. Manmohan Singh in December 17, 2005. So, Raja Ramanna Center for Advanced Technology is spread over a 760 hectares of picturesque site, and the campus has its laboratory areas, staff housing and various basic amenities. And two major programs of RRCAT includes research and development of accelerators and lasers. The accelerators includes Indus 1, which is a 450 MeV synchrotron radiation facility, and Indus 2, which is 2.5 giga electron volt synchrotron radiation facility. These are the national synchrotron radiation facilities. And then we have free electron laser and electron RILNAC. So in lasers, we work on development of variety of lasers from gas lasers to solid state laser, chemical lasers, semiconductor lasers, and their applications in variety of areas, and also biophotonic systems. So the core programs at RRCAT Indore includes synchrotron radiation sources and free electron lasers, their development and their applications in material research and medical research, development of high intensity superconducting proton accelerator technology for actually this technology is to meet the third stage of the Indian nuclear program at an early time, and this requires the high energy 1 GeV proton beam for SNS, and then there are electron and proton accelerators for societal application, which includes irradiation of industrial products and food processing, and lasers and their applications in different areas. And then RRCAT also participate in various international organizations for such as CERN, Fermilab in USA, and then for project on LIGO and FAIR, I'll give a brief glimpse of these in the next coming slides. So this shows the schematic of synchrotron radiation source at RRCAT. This is a national facility, and this is continuously operated since 2010, and they are used by in-house as well as external users. So the basic setup is shown here. The electron source is microtron, which generates 20 MeV of electron at 30 milliampere, which is fed into the booster ring, where the energy is boosted up to 550 mega electron volt, and from here it is fed into Indus 1 ring, where its current is increased up to 125 milliampere. So Indus 1 is the synchrotron source 1, which operates at 450 mega electron volt, and it generates light from mid IR region to soft X-ray region with a critical wavelength of 61 angstrom. And then this 450 MeV 125 milliampere electron beam is transferred to the Indus 2 storage ring, and then is accelerated with the help of bending magnets to 2.5 giga electron volt and 200 milliampere. So at the bending magnets, we get a broad spectrum of light which covers soft and hard X-ray regions with a critical wavelength of 2 angstrom. So at each bending magnets of Indus 1 and Indus 2, we have various beam lines which are used for different experiments. So you can see this is the Indus 1 storage ring. It is a 19-meter storage ring, and it is all vacuum pumped up to 10 to the power minus 10 millibar. So you can imagine the complicacy. And then this is the view of Indus 2 tunnel. So this vacuum tunnel is 172 meter in circumference, and this is the experimental hall where these synchrotron radiations are made available for various spectroscopy and other condensed matter physics experiments. And you see the number of experiments since 2016 which have been carried out on these synchrotron radiation sources. You can see it has continuously increased over the years. Also there was a dip during the corona period, but now it is again picking up. And the right handmost picture shows the number of publications coming out using the synchrotron radiation sources. So one can see that with the time it is continuously increasing, and even there was a corona crisis and research work was impeded, but still publication has increased, and we expect that with, in coming years more and more users will be using the synchrotron radiation for their research, and recently companies have also started coming for their R&D applications. So this slide shows the operational beam lines. So Indus 1 has 7 beam lines at these bending magnets, location of bending magnets. So these are the high resolution VUV spectroscopy beam line, then angle integrated photoelectron spectroscopy beam line, soft X-ray reflectivity beam line. So these are the various beam lines used for material research and spectroscopy purpose. And Indus 2, which is 2.5 GeV synchrotron source, has 17 functional beam lines, and few are about to come, and they include this soft X-ray absorption spectroscopy beam line, and then beam line for engineering applications, X-ray imaging, X-ray lithography. These are the advanced area in material science and device fabrication. And then spectroscopies like dispersive and scanning, X-ray fluorescence spectroscopy, and then angle dispersive XRD, and protein crystallography, X-ray diagnostic, etc. So 17 beam lines are currently function on Indus 2. So this is another equipment developed by laser group at RRCAT working on biomedical application. So they have developed a standalone biophotonic instrument for detection of oral cancer in a non-invasive way. So you can see this image, such a compact system, and it is based on the fluorescence measurement. And as we know, in case of cancer in the oral cavity, one way, clinical way, is to go for biopsy, and that is a time consuming and cumbersome process. So a laser fluorescence based standalone system have been developed where we can predict the cancerous tissues and beginning of cancer in the oral cavity in a very short time of 15 minutes, and we have found through various testings in the hospitals and laboratories that it has accuracy more than 90% compared to the pathology testing. So with the time it has been developed, and now it has been made available to various hospitals at remote locations. You can see this has been possible because of its compactness and standalone nature. Laser fluorescence imaging based TB diagnostic measurement, tuberculosis diagnostic system has also been developed, and the conventional technique rely on fluorescence microscopy, and that is time taking, and compared to that fluorescence imaging was used to detect TB with the equivalent accuracy but at a very low cost and in a low time. So this is now available in a compact form to various hospitals for detection of TB. And this is the equipment developed during the COVID time. We all saw the hotspot situation during that time, and it came out that irradiation with deep UV light is facilitating this reduction of this COVID-19 virus. So a Neil Bhasmi setup was developed for laboratory and office uses, which is equipped with 8 UVC lamps at different arms, and you can see this is the image when it is folded, and this is the image when all arms of this equipment are open. So this is used for sanitization of large area, office area, or various office files, etc. And it is movable and can be mounted on trolley also. So another area where RRCAT is contributing is electron irradiation of food items. So as I mentioned, one way of irradiation of food commodities is gamma radiation obtained from C60 isotope. Another way is to irradiate these food commodities or medical items with 10 mega electron volt electron irradiation. So for this purpose, RRCAT has developed indigenous electron beam irradiation facility near the go back. Near the Choithram Mandi, you can see this is the premises, image of the premises, and this is the image of the system which is used for irradiating the food commodities and various items used for medical purpose such as syringe and packaging and gloves, etc. So electron irradiation has come up as a more affordable radiation process for these applications. Infrared free electron laser is another area where RRCAT is working, and it is a national facility in that sense. So it generates terahertz and infrared spectral region photons, and this is used for spectroscopy. And this is the image showing the linear electron accelerator, which is used for generation of free electron lasers. So RRCAT is also involved in the development of variety of lasers and their application in industry, medicine and research. So the type of laser developed, as I mentioned, gas laser like CO2 lasers and excimer lasers. Then solid state laser, which includes flash lamp and diode laser pumped and diag lasers. Then semiconductor lasers, chemical lasers, and excimer lasers, etc. Various industrial applications have been developed and demonstrated, which includes cutting, drilling, welding, surface modification and rapid manufacturing of material. Then laser based instruments, specific instruments such as uranium analyzer, land leveler, photocoagulator and fiber based temperature sensors, etc. have been developed, and some of these lasers have been supplied to hospitals also for surgical purpose such as CO2 laser. And then we use homemade and commercial lasers for research in various areas, including laser plasma interaction, laser based charge particle acceleration, laser fluorescence spectroscopy, nonlinear optics and material processing, etc. So these are the images of laser developed at RRCAT. So this shows the 100 watt copper vapor laser is having wavelength varying from UV region to visible spectral region, and then it is an image of diode pumped 1 kilowatt CW NdIAG laser developed for a specific purpose, and then this is 500 watt fiber laser developed for some departmental requirement at nuclear power plants, and then this is 2 kilowatt RF excited fast axial flow CW CO2 laser for material processing and medical applications. So 5 kilowatt and 10 kilowatt fiber optic beam delivery systems and fiber optic lasers have also been developed for material processing and various works related to material cutting and welding at nuclear power plants, and they are utilized at different power plants in a very efficient way. Laser additive manufacturing is another area where RRCAT is contributing significantly. It's actually a 3D printing method where laser is used to vaporize and melt the material and deposit at a specified locations. So in this process we can grow the structures, metallic structures, complex metallic structures starting from scratch, and this approach is different from this bottom down approach. Rather it is called top-up approach. We start from the scratch and start building these complex structures such as these mesh and these bushes and these joints. These are required for specific programs of Department of Energy, Atomic Energy. And this is a bone implant which is developed by using laser additive manufacturing technique out of titanium metal. Yes. And then fiber brag gratting, lasers and sensors, they are very upcoming area, and RRCAT has expertise in the development of different kind of fiber brag gratting these fibers, and their applications in temperature and pressure monitoring. So the areas where these fiber sensors have been used includes railway, where these sensors are installed on the railway track to measure the impact load, which is very important safety feature used by the railway. And then this is fiber brake gratting sensors mounted on the brake level of train wheels to measure the brake force generated during the braking process. And then these fiber gratting based temperature sensors, which are very accurate, they are also utilized in Indus 1 and Indus 2 for measurement of temperature. So in addition to the various societal activities which I have discussed, the Raja Ramanna Center for Advanced Technology have various international collaborations. These includes collaboration with CERN and collaboration for LIGO and then FAIR. So these are the collaboration where RRCAT is actively involved for the mega projects. So LIGO, as you know, it is a laser interferometer based gravitational wave observatory, and this has been used to detect for the first time the existence of gravitational wave. And it has been decided that other than the two LIGO units which are in USA, there will be one LIGO observatory in India, and RRCAT is the major contributor into this development of this LIGO observatory. So the basic principle of operation of this LIGO interferometer is shown here. It is based on the interference process, and you can see this is the arm, around 4 kilometer arm length, all vacuum, where laser travels, and then there is a end mirror. Similarly, there is a 4 kilometer arm at 90 degree to the first arm, and again the laser starts, and with the help of end mirror it is reflected back. So when the distances are perfect, the laser returning from this first end mirror and this end mirror will meet in the same phase, and or they are so tuned that they meet in the opposite phase, and therefore there is a total dark. And if gravitational wave passes through Earth, there will be distortion in the optical path, and that will generate a phase difference or path difference, and as a result, at the point of interaction, that is at the photosensor, which is a very sensitive photodiode, there will not be complete destructive interference, rather we will have some light which will be detected by this photodiode. So in this way, this gravitational wave disturbances are measured by this LIGO facility. So India is developing third LIGO facility, and first in Asia and first in India. So this is one development from cryogenic group at Raja Ramanna Center for Advanced Technology. We have all witnessed the requirement of these liquid cooled refrigerated vehicles for the transportation of vaccines during the corona time. So a new technology has been developed which is based on the liquid nitrogen for the refrigeration and storage, and this is known as Sheetal Vahak Yantra, that is Shivai, and now it is developed in a complete form coupled with the truck with the help of Tata Motors, and it is now available for transportation of various goods and medicines in the conditions of low temperature. So now I will discuss the career opportunities for the young science and engineering graduates in Department of Atomic Energy and RRCAT Indore. You can see the picturesque image of RRCAT campus. This is Indus building containing the synchrotron radiation sources. This is the image of palace where light exploratorium has been developed recently, and this is the view of beautiful view of the lake, and of course natural beauty you can see around RRCAT campus. Yeah, next please. So this slide summarizes the career opportunities at Department of Atomic Energies. So engineering and science graduate having 4-year B.Tech, BSc engineering degree, or 5-year integrated M.Tech or MSc in science stream can apply for BRC training school at RRCAT and other DAE units. So in the BRC training school, the selection of scientific officers is done in a centralized manner by Bhabha Atomic Research Center, Mumbai, for all BRC training institutes situated at various constituting institutions such as RRCAT and IGCAR, etc. And then there is a 2-year DGFS program, that is DAE Graduate Fellowship Scheme for engineering graduates, and the stipend during the training period, 1-year training period, is 55,000 per month for OCES and DGFS. It includes book allowance of 18,000 and then tuition fee and contingency grant of 25,000, etc. And the detailed information about the BRC training school program, intake program, can be obtained at this URL, brconlineexam.in, and normally it is announced in the beginning of every year, and exam is conducted sometime during March or April, and interviews are conducted June to July. So another stream which gives opportunity to PhD holders or master's degree in engineering with 2 years of R&D experience to join as a scientific officer in Department of Atomic Energy through K.S. Krishnan Research Associateship. So detailed information about that K.S. Krishnan Fellowship can be obtained at this at the website of BARC. And then graduates in science and diploma holders in various engineering branches are recruited through 2-year stipendary training program, and they are absorbed as scientific assistant C, and then they proceed in their career as D, E, F, etc. Another mode of joining at a technician level, candidates having qualification of HSC followed by ITI certificates, they can be recruited under a 2-year stipendary training program and they are absorbed at technician B or technician C positions in various units. So RRCAT also is involved in conducting PhD programs through Homi Bhabha National Institute, and Homi Bhabha National Institute is accredited with NAC A grade and is an institute of national importance. And then there are projects available for students of MTech, ME, MPhil and MSc degree, those who are in the final year of their degree program. And then yearly we have a orientation course on accelerators and lasers, where graduate and master students from science and engineering students are given training for 1 year in the advanced areas of lasers and accelerators. And then there is a young scientist research program especially for undergraduate students. This is conducted every year, and good number of students are selected for doing their project work during the summers, that is from May to July of every year, and mainly the students from third year of and fourth year of BTech in each scheme, in each stream, they are selected for YSRP program. So Homi Bhabha National Institute, as I mentioned, it is deemed to be university and it is an institute of national importance. This is the image of the Homi Bhabha National Institute campus situated at RRCAT Indore, and it runs various academic programs starting from MTech, MPhil, PhD, and then integrated PhD programs, MD, and 5 years integrated MSc program in its various institutions, including from NICERS to IPR to IRRCAT, etc. So with this, I come to the end of my talk, and various useful websites which you can refer to get more information about the Department of Atomic Energy and RRCAT are listed here. For RRCAT, it is rrcat.gov.in. And with this, I thank you all for your patience and listening me. And if there are any questions, I will be happy to answer.
Thank you very much, sir, for a wonderful lecture. Any questions? Yes, ma'am.
What's the procedure for selection in orientation program? Can you please highlight that for the students?
Yes, actually, national level entrance test is conducted every year, and based on the result of this entrance test, which is a written test, certain number of students are selected, and then they are called for interview at various DAE locations. And for this process, DAE provides true and fro fare and accommodation for the interview period. And through interview process, required number of candidates are selected, and they are assigned to different DAE institutions for 1 year training program. So on successful completion of 1 year training program, they are appointed as a scientific officer, irrespective of where they have done their 1 year training. So this is the whole procedure for 1 year orientation course, and such courses are running on in every DAE units, including RRCAT. You have completed the bachelor's, final year. So as I mentioned, young scientist research program is designed for final year students for pursuing project work in these national laboratories for 3 months. So I think since last 2 years this program was not organized due to COVID, because experimental work is not possible in online mode. So this year we are planning, and you keep on watching RRCAT website. Because of COVID there is a delay in the program. Normally it happens from May to July, but it is delayed. But every year during February to March there is a separate advertisement for YSRP program, and around 20 students are selected from science and engineering stream to do their project work at RRCAT, and we provide accommodation as well as fellowship during the entire period of project work. Pardon? This year till now there is no advertisement, but please keep watching the website. In coming 1 month, maybe there will be advertisement for winters for 1 month or something, because this summer we could not utilize through this scheme.
Sir, as you mentioned that we treat our food for, sorry, that means. So like we treat our food and stuff with radiation to kill the harmful bacteria, but doesn't it changes the food, like it makes the food radiated, like radioactive, and will
Yeah, that is actually a very good question. Normally this radiation treatment only eliminates these germs and bacteria, and these radiations have certain penetration depth, and through various rigorous experiments it has been found that there is no negative effect on the food commodities. There is no change in the taste of material, its nature, its fragrance. Rather, it can give some beneficial effects in some items. As I mentioned, if you see potato, the major problem with the storage is that it sprouts, and once it sprouts, it is difficult to store it for longer period. So it has been researched that irradiation with gamma radiation or electron beam slows down this sprouting process. So as a result, their storing period can be enhanced. So a lot of wastage can be prevented. So there is no adverse effect of this radiation dosing on any food item which atomic energy is doing, and actually they are adopted by many industries, not only in our country but worldwide.
the current trends is like we are shifting from nuclear energy to more green energy like solar and wind and even tidal forces. So is there like any effort from Department of Atomic Energy in that area?
See, as I mentioned, to meet this gap of energy requirement and the energy which we produce, we have to utilize all the sources of energy, whether it is conventional by using coal plants or by using hydel plants or by using solar cells as you discussed. Unless we use all of them, we cannot meet the requirement. But since the requirement is huge, so there is a big role of nuclear energy to meet these numbers. Okay. Any source alone cannot meet this requirement.
And the last question, like I am from the physics department, so I know that after this like making of the energy, there is some radioactive waste in the nuclear power plants. So how do we treat those? Like in India, like we like in general we know that we dump some of that in our oceans and somewhere. which makes the ocean life very bad. But do we like have any solution for that? Like
Yeah,
treating the-
actually, see, this is again a important question, and every nation has its own policy of nuclear waste management. Some countries, they dump it either in ocean or at some remote place. But as far as India is concerned, we have decided for recycling of the nuclear waste. And we take important isotopes out of that through rigorous reprocessing facilities which are developed over the year, considering our nuclear programs. So yes, we simply don't dump, we process these nuclear waste and get maximum out of that. For example, in this nuclear first stage programs, which is based on uranium itself. So here, apart from energy, there are other byproducts also, out of which one is plutonium. And that plutonium we cannot simply let out to go. So a rigorous process has been evolved to do this processing.
Okay, thank you very much, sir.
हाँ सर, हमारे स्टूडेंट्स कैट में प्रोजेक्ट करना चाह रहे हैं, एमएससी के स्टूडेंट्स हैं, तो उनके लिए क्या प्रोसीजर है, प्लीज़ स्टूडेंट्स को बता दीजिए। थैंक यू सो
या
मच।
वो किस स्ट्रीम से हैं?
सर केमिस्ट्री वाले तो हैं ही, साथ
जी
में मुझे लगता है फिजिक्स और बाकी जो स्ट्रीम्स हैं वहाँ भी अगर अपॉर्चुनिटी मिलती है
जी हाँ।
तो स्टूडेंट्स करना चाहेंगे। तो सर
देखिए,
वो-
हर साल लगभग 100 से 150 मास्टर स्टूडेंट्स अपने प्रोजेक्ट के लिए आरआर कैट में आते हैं। हालांकि कोविड की वजह से ये संख्या पिछले 2 सालों में कम हुई है, लेकिन इस साल से वापस से स्टूडेंट्स का आना शुरू हुआ है। तो ये जो मास्टर्स लेवल पे एमएससी फिजिक्स, एमएससी केमिस्ट्री, एमएससी बायोलॉजी और बायोटेक्नोलॉजी, इन सभी एरियाज में प्रोजेक्ट वर्क की अपॉर्चुनिटीज़ है। 6 मंथ की प्रोजेक्ट्स होती है एमएससी के लिए, और अगर आईपीएस इस इंस्टीट्यूट से अप्लाई करना है तो इनफैक्ट उस एडवर्टीजमेंट का भी वेट ना करें। आप जिसको भी जानते हैं आरआर कैट में, उसको मेल लिखें, क्योंकि कई बार ये समर प्रोजेक्ट्स या 6 मंथ प्रोजेक्ट एक ईयरली 2 बार प्रोसेस के तहत एडवर्टाइज करके किए जाते हैं, और कई बार स्टूडेंट की रिक्वायरमेंट और स्टूडेंट और प्रोजेक्ट की मैचिंग और सुटेबिलिटी के आधार पे अदर देन दीज फॉर्मल रूट्स भी पॉसिबल हैं। सो इफ समवन इज हैविंग सम गाइड इन हिज माइंड वेयर ही कैन वर्क, and in this case faculties from IPS Academy may guide the students. So students can write directly to the faculty, and faculty will definitely guide them to apply with the procedure to a certain person who will shortlist and finally announce the result. But I can give a rough number that from whole country, mostly students are from nearby places, but around 100 to 150 students do their MSc and MTech projects over the year in RRCAT. And formal advertisement comes out on the RRCAT website. You can see under the section opportunities. So this is there.
Thank you very much, sir, for your wonderful lecture and making us aware about Department of Atomic Energy and RRCAT and all the various research projects, activities going on nuclear power plant, waste management, environmental project, and making us aware about Indus 1 and Indus 2. And most of all, about telling us about the career opportunity which are beneficial for our students. So thank you so much, sir, for your lecture. Thank you once again, sir. Again, we have one more eminent speaker among us, Shri Govind Panchari ji, Head CSD and Chief Engineer RR-CAT, completed BE Civil in 1987 from SGS ITS Indore, worked in Gilcon Project Service Private Limited. In 1989, he was selected for oriented training course from Bach Training School. He completed ME Structural Engineering 1997 from SGS ITS Indore. Currently, he is heading construction management of R&D labs. He has been a key person in successful completion of planning, design and constructions of number of R&D labs for laser and accelerator program, including Indus Complex. He has been seeing the construction program for about 60 buildings, having integrated service for civil, electrical, HVAC and horticulture, etc. He has recipient of many group achievement awards, in addition to Group Leader Award and Department of Atomic Energy Excellence Award scheme from adopting novel technique of economic designs and construction of conventional schemes, conventional center at township. With Swachh Abhiyan consequently for 4 years. In addition to this, he has published more than 30 research papers in various conferences. So I invite you, sir, for your lecture today. Please give them him up. Thank you, sir.
Thank you all. Without wasting time, with thanks to IPS Academy, I will just start my lecture. Yeah. Yeah. On. Okay. Yeah. We are celebrating 75 Azadi Ka Amrit Mahotsav and DI Iconic Week. I will be talking about next slide. So on a topic of concrete as versatile radiation shielding material. Actually, we have seen that we in RR-CAT and DA we have the specialized structures, nuclear facilities. These structures have special requirements for buildings also, and one of them is radiation shielding. And radiation shielding is not especially uncommon, and that we have to do for our projects. Next, please. You'll have to go fast. Yeah, so the outline of my topic is objective of biological shield, radiation structure interaction, radiation shielding planning and design, how it is done, different types of concrete for radiation shielding. We have seen concrete as a common building material, but here we are discussing concrete as a radiation shielding material. So we'll see the different types of concrete for radiation shielding, concrete as a versatile radiation shielding material, concrete mixed design for high density concrete because this is important for nuclear structure, a special feature for building planning. Such buildings needs to be planned with a very careful design and all that, so that radiations are taken care, radiation levels are taken care. And again we have seen Indus 1 and Indus 2. I will be giving some details about the Indus complex also. Radiation shielding, the objective is that we actually we have to take care of radiation because these are harmful to the people, the persons who are working in the facility and around. So we have to provide a shield so that the radiations levels are brought to So these radiations are to be actually brought to the permissible level so that they are not harmful for the persons. Now, what are the things which are depending upon this? Three basic factors are there for radiation protection. One is time. If the time of exposure is less, then it is more harmful, and if it can be reduced, it is good. And distance, the radiation actually follows the inverse square law for the propagation, and the radiation levels goes down with the distance as inverse of the distance. And see the interaction of radiation with matter. When the radiation interacts with the matter, it becomes itself a source. So direct ionizing radiations are there. Many of us know about the direct ionization radiations, like alpha radiations, beta particles. See, alpha particles, alpha radiations are high ionizing energy, low penetration level. These have the low penetration level. Maximum range in air is 4 MeV. Alpha particle is approximately 2.5 centimeter. It can be stored by sheet of paper. That means these are the heavy particles, but can be stored by smaller thickness of object. Now the beta particles consist of free electron particles. These are high penetrating power and can be few meters in air and can be stored by 1.5 centimeter thick of lead. Next please. Indirect radiations. These are basically the neutron, gamma rays, X-rays, photons are not charged particles. They bring ionization by causing emission of secondary particles. When they interact with the particles, then they give out another radiations. These photons are basically the electromagnetic radiations, and these are called photons. And we have studied even in school level, its energy is h nu, that is the energy of the particle. Gamma rays, the photon origination from the nucleus, because we know that from the radioactive that alpha, beta, gamma, these are the radiations which are come out. These gamma rays are coming out of nucleus, and this photon energy is greater than 0.1 MeV. MeV actually is a million electron volt. If in a simple manner, I try to explain what is electron volt, it's the unit of energy. If there are two, one is cathode, is another anode. These are the two, and if there is a voltage difference is 1 volt. Then if electron moves from cathode to anode, whatever energy it gains, it is 1 electron volt. Now you can understand the level of energy in terms of million electron volts. X-rays consist of electromagnetic radiation, but energy of these photons is less than of gamma radiation. Next please. This slide shows the different characteristics of alpha, beta, gamma rays and neutrons, and this shows that these particles how it can be attenuated. This is just giving a reference that how much powerful which particle is. Next please. See, I am skipping because I want to come to the civil structure. So this is another way of graphical presentation of alpha, beta particle, neutron, gamma rays and X-rays, and how these can be stopped and how heavy and how different are these. Next please. Yeah, now I am coming to the main topic. It is radiation shielding, planning and design, how it is done. Radiation shield is a physical barrier between source of ionization and the object to be protected, so as to reduce the radiation level at the position of the object. Salient features, how it is, how the building is planned. So we follow the zoning philosophy. I will give detail in next slide. Exclusion zone. We in nuclear reactors, we go for containment structure. That means we have the two structures with an annular space in between. We take care of the radiation streaming at the areas of penetration. So detailing of penetration is to be done in a careful manner. Design for uncrashed condition. I think from civil engineering stream, there are students are there. They will be able to understand. We normally design any RCC structure for some crack width permissible. That is 0.3 mm. Ordinary structure we design for 0.3 mm crack width, but here we have to design for uncracked condition. So because there is a question of streaming of radiation, so we need to design for uncracked condition. Provision of services. Actually, when we plan a big facility, then we need to take care of the provision for services, future upgradation, because technology is changing very fast, and we may have to upgrade the facility in future. Next please. Yeah, I was talking about zoning philosophy. So you can see here is that zone 1, 2, 3. So actually the building is planned in such a way that there is no entry in zone 3. Zone 3, which is the machine or the facility which is having more radiation level, are kept inner side, that is landlocked. It is landlocked. And zone 2 is the restricted entry. These are the areas where only operating personnel are allowed to go. Zone 1 is normal occupancy zone, where there can be occupancy. Next please. Yeah, design philosophy wise, as I said, if I want to design a radiation shield, I have to know what is the source and barrier we have to design, object to be protected. These are things are to be there. How the radiation level changes, this equation gives when there is a intensity of radiation is I0, and when there is a barrier of thickness T, then after the thickness T, after the barrier, the intensity of radiation will be I is equal to I0 e to the power minus mu T. That means it reduces in exponentially. Now there is a terminology about TVL you must be seeing here, that it is 10th value layer. The radiation reduced to the 10th value of the original intensity is called the thickness required, and it is named as 10th value layer. Next please. So how basically now I am giving focus to the electron accelerators, that how the radiation shield is designed is that one we have to calculate the electron beam loss scenario, that what is the dose, what is the intensity which is to be reduced. Then we do some tentative building planning is done. Then depending upon the nature of radiation, latest design, component design and modification, we carry out the building design. Then it is given to the Atomic Energy Regulatory Board that these are the level, these are the building plans and how it is going to be there. Then these are then in machine operation and commissioning. Even we have to obtain approval for before even the commissioning. So there is a construction clearance required, and after that we go for commissioning, and after commissioning also there is a approval required. Next please. Now shielding design can be done manually also, but this shielding there are computer software available. Fluka is a software which is used for calculating the radiation levels by putting a barrier, how much the level can be reduced. So giving the properties of barrier and intensity of the source, one can calculate the radiation level. Next. These are the different, now we are coming to materials. These are different materials which can be used for making a radiation shield. Now this depends on the type of radiation also, this depends on the value of radiation also. So materials which are now used are the concrete, lead, steel, densimate. Densimate is nothing but tungsten 95%, so and Pervex acrylic. These are having the different type of characteristics and their applications also. So for example, concrete is best for Webster-Lang radiation, photons, electrons, positrons and photoneutrons, and its density is 2.5. It is a normal density what we normally undertake adopt for the building construction. It is economical, good, and it has got a moldability also, and ability to cast in different densities also. This concrete can be given a higher density by choosing high density aggregates. Then okay, and then lead also is having a density 11.35 gram per cc. It is good casting ability. Actually this can be cast into blocks also, bricks also, which can be, and this can be used in the form of shots also, sheets also, wool also. So these are used for Webster-Lang and photons arresting. And we can, how the quality check is done also, it is given the dimensional density check also can be done, NDT can be applied for checking this thing. Density is an important property for radiation shielding, and one has to take care of this. And steel is the another material which is used. Actually this steel is common, this is actually very costly, so concrete is compared to the concrete, it is costlier. And also there are different properties of concrete which are more useful for attenuation of neutron. In fact, concrete is more useful because concrete has water in it. After cement hydration, there is a water in gel pore, there is a crystalline water also, and water has hydrogen which has got very good cross section for attenuation of neutrons. So whenever there is a question of attenuation of neutron, and then concrete comes on first, as this is better than steel. Perfect acrylic, okay. Okay, next please. So these are actually these slides give some attenuation coefficient. Actually, how we define the radiation shielding property, like we define the property of concrete for mechanical properties as a strength of concrete, characteristic strength of the concrete, compressive strength of the concrete. Similarly, if I want to define the characteristics or the properties of shielding material, it is defined as the attenuation coefficient. So these are the attenuation coefficient we have seen in the this formula. I is equal to I0 into e to the power minus mu t. Mu is that attenuation coefficient and t is the thickness. So this together actually decides the type of reshield. So if we see concrete has got a if it is having a normal density concrete, it is having a mu 4.04 and its 10th value layer is 0.57. 10th value layer, again I will again explain, this is 1/10 the thickness required to bring the radiation level to 1/10 of the original. So similarly, other materials also the density for different type of radiations it is given. So what we can conclude is it is not that the thickness or density only is the parameter which decides the selecting the radiation shielding material. It is the type of radiation as well as the intensity of the radiation which is to be taken care of. So concrete actually, concrete again can be, because as I said the concrete has an ingredient of coarse aggregate, fine aggregate, cement and water. So here the maximum proportion of the ingredient is from aggregates. So if we change the aggregate of higher specific gravity, then we can have the heavy density concrete which will be more useful. The density of concrete will be more and the attenuation coefficient also accordingly will be more. Now next please. There are some special concretes also. See, as I said that concrete has hydrogen in it in the form of crystalline water. So if hydrous aggregates are used and these will if they can retain the more hydrogen or water in concrete in stable form, this will be very useful. So actually serpentine concrete is using the serpentine aggregate as a ore, but why these are useful again, because we have to see another condition is that when the temperature is high, then that time the water will get evaporated from Jaipur also. So in this case the stability, the water stability is important, and these are the ores which retains the water even at higher temperature. So that is why these are of concern, and this is a good property of these aggregates which makes them suitable for the reactors. Next please. So this slide summarizes that how the concrete is a versatile material. It is a very good radiation attenuation material. It is having mechanical strength. See, for example, if I say water, see I say that for neutron, the hydrogen has the best cross section for attenuation. So water could also be used because water itself has a lot of hydrogen, but water does not have the mechanical properties. So these are the differences. So and where this concrete has the mechanical strength also. So for making any structure you need a mechanical strength also. So this is having a mechanical strength as well as radiation shielding properties. So that is better. Can be cast in different shapes. Why this is important? Because many times we have to cast concrete in intricate shapes depending on the facility design. So and concrete has a flexibility to cast into the different shape because it can be molded with in the formwork. It possesses crystalline water, as I told. Economical, actually, if you compare to the steel or any other material, it is economical, and because it is all locally materials are available, and these are one can manufacture as per the requirement. Need special care when used. Actually, concrete is a heterogeneous material, so we'll have to take care of while making is for radiation shielding concrete. It has to be homogeneous. So testing is to be done for its homogeneity, and NDT can be done for that. And we have to take care of the joints also, because there may be cold joints, and cold joints may lead to streaming of radiation. So the joints have to be staggered. There is a special feature of that, how it can be done. There is all procedure is there that can be done. Concrete may have cracks of shrinkages due to shrinkages. So what, because this, when you use the radiation shielding concrete as for shielding, this requires a large thickness, and when the thickness of concrete becomes more, it has a heat of hydration which is generated at the core of the concrete and does not get dissipated, and which has then delta T. The temperature of core is more compared to the surface, and because of delta T, it has a thermal cracks developed. So in order to take care of this, we have to cast the concrete at controlled temperature, so that the temperature generated at the core is less and delta T is less. So as we normally do the concrete at ambient temperature, so this is not allowed in case of where you are going for a radiation shielding concrete. You will have to go for a chilled concrete. But again, we cannot use ice as for chilling the concrete, lowering the temperature. Because ice piece may remain as it is, and afterward it may form a cavity which is not desirable. So if at all we have to use the ice chilled water, or we can use ice flex. Flex can be used, but we cannot use ice blocks. So ice blocks can form a cavity, so that is not required. Next please. So this is about concrete. Mixture of, actually it's a mixture of cement, fine aggregate, corrugated water, and when it mixed in designed proportion, it turns to a solid mass which has a mechanical properties. What basically goes when cement hydration takes place, this cement has compounds dicalcium silicate, tricalcium silicate, tricalcium aluminate, and tetracalcium aluminofluoride. When this reacts with water, this forms the calcium silicate hydrates, which is gel, and as a byproduct it forms calcium hydroxide also. Now here the importance is that say the compounds which are there in the cement, in this the one component is there C3A, which is basically gives which evolves heat at the time of hydration. So this content of C3A should be low. In large mass concretes, normally we prefer to have the low heat cement, and low cement is nothing but the same cement with less percentage of C3A. Next please. Now how shielding thickness can be determined? So actually mu, as I said, it is the attenuation coefficient. So mu, if it is divided by the density mu by rho, it is called mass attenuation coefficient. And for different intensity of radiations, there are mu by rho is defined. So if any of my matter is having this elemental composition, if I know about mu by rho of the elements for that radiation intensity, I can work out the radiation attenuation coefficient, because it is a weighted sum of mu by rho, and you can just calculate and you can find out what is the mu by rho of the mixture. Next. Type of cement, gradation, grade designation. Actually this actually when the strength is not a primary concern for when we are going for radiation shielding, but indirectly it is there, because we are using it as a structural element also. So minimum grade is required, that is to be provided as per IS code, as you may be knowing. And type of cement, I said that it should be either can be OPC, but see if low cement is available, it is good. Otherwise OPC can be used with the chilled concrete. That means if you are placing it at a lower temperature, it can be used. Maximum nominal size, water cement ratio, these are the normal things which we do. Actually even heavy density design also is, we are following the same procedure. There is a difference, there is no difference in mixed design of a ordinary density concrete and a heavy density concrete. Next please. This I will skip. This is actually this is how the mixed design of a concrete is done. So this is based on the absolute method, and actually we work out the proportion of the concrete, different ingredients we work out, and water cement ratio is one of the most important parameter on which the strength of the concrete depends, and by that we go by that, and water cement ratio required for particular strength we select, and then we require water content for workability, work out the cement content, and from absolute method we find out the other ingredient. Yeah, there may be a question that what is the difference between normal density concrete and heavy density concrete. So heavy density concrete, actually what is the difference is only of the coarse aggregate, and coarse aggregate we replace by the conventional aggregate we replace by the coarse heavy density aggregate. So question of availability of coarse heavy density aggregate is a concern. See, if you are having a locally available high density ores which can be used for coarse aggregate, it will be cheaper. But in general case, it is there is a graph given for concrete density versus the cost, and if you see from this graph, it is heavy density concrete is 7 times costlier compared to the ordinary density concrete. But you are not getting that much gain in the radiation shield. So the conclusion is that wherever there is no constraint of space, ordinary density concrete is preferable. Right. So ordinary density concrete comes to cheap, economical, and but what is that which we are missing in the ordinary density concrete? The thermal conductivity of the ordinary density concrete is less compared to the heavy density concrete, because we are using in heavy density concrete as a heavy aggregate like hematite, magnetite. These ores are used, and these are having the higher thermal conductivity which is required in case of reactors. That is why in reactors high density concretes are used. Next please. Yeah, there are some guidelines from National Council on Radiation Protection and Measurement. So we will see that the type of radiation and location of source, the emission rate of radiation reflected. See, the best advantage of the radiation, what we can take the best advantage for radiation shielding is that radiation travels in a straight line. So whenever we design the nuclear facility which are supposed to attenuate the radiations, we provide we design the place in such a way there is even after the reflections the radiations comes to a lower level. So many number of times if the radiation sees reflection, that is considered better. Next. These are some guidelines given. See, if you are having a building, it is not only the building on the sides of the building which is to be seen for the radiation source, but you have to see the adjoining buildings also and the first floor also if there is occupancy. So one has to design, if something is there in the basement also, you will have to design the floor or ceiling also to take care of the radiation attenuation. Next please. So these are the typical layout given for entry into a radiation shielded area. It is not straight, like if you enter into any room, you just have a door from the corridor and just enter it. But if you want to enter in this type of structure, then you will have to go in zigzag manner. This zigzag manner basically actually just to have to create more and more number of reflection, so that once these radiations comes out, they are of less intensity. Yeah, actually I said about sky shine. See, there is a source. If there is a source in the building, so it is not giving. There is by the side of it is a controlled area. There will be some radiation level, but this radiation may not be directly from the machine itself, but radiation source itself, but also maybe apart from contributed from the sky shine. So we have to see what are the radiation level up on the ceiling side. Next. Now, there are some requirements in any shielded area that we will have to have some openings. Sometimes you have to have, let's say, as we have seen in the last slide that we had a zigzag cell. Suppose that much space is not there, then you will give a sliding door. But then sliding door also should not result into the streaming of radiation into the adjoining area. So there are some guidelines which are given, which we have to follow, is that sliding gap, whatever the gap is there, 10 times of this gap width, the overlap length has to be there. So because of this 10 times length, it will see number of reflections, and when it will see number of reflection, the intensity will go down. So wherever there is a space problem is there, and we are not able to give a zigzag, so basically zigzag shape we give a terminology labyrinth. So if you are not able to construct labyrinth, then shielded doors can be provided, but with a gap overlapping. This shutter has to overlap on the solid part by a length more than 10 times the thickness. Again, the lower picture shows the plug door. You can see this is not directly a square block which is plugged into the wall. It is having as offsets. These offsets basically helps to avoid the clean joint, and accordingly the streaming of radiation is not there. So in order to attenuate the radiations, what we have to give is that we have to give the offsets into the plug also. Next please. Yeah, actually Indus 1, Indus 2 we have seen, we were discussing since morning also. So this actually, you must have seen the upper figure, because that is a schematic of the Indus 1 booster Indus 1 and Indus 2. And here on the right side I have indicated the building drawing also. So you can see this Indus 1 and Indus 2. Indus 1 is a rectangular block which is having microton, and from booster you can correlate it with a hexagon lattice, which the electron beam is taken into the transfer line 3 and Indus 2. These are the blue lines which are tangent lines, which you are seeing are the actually synchronous radiations beam lines which are coming into the experimental hall and which are being experimented for different purposes. So actually this to give you some idea about the Indus 2, this what annular ring we are seeing in the center, it is having annular space to house the Indus 2 machine with RCC concrete wall of 0.6 meter thick inside and 1.5 meter thick outside, because outside is actually adjoining to the experimental hall, and inside wall is basically unoccupied area. So there nobody is allowed to go when the beam is machine is in operation. So actually the 1.5 meter thick wall is on experimental side, which attenuate the radiations to the permissible limit, and then we can and the ceiling also is 0.6 meter thick. Next slide. Yeah, as I said, can you just go back? So here also you can just correlate what we were talking about zoning philosophy. So you can see that zone 1, zone 2 and zone 3 are clearly marked. The central space which is unoccupied, and after that the Indus beam and Indus ring is there, that forms a critical zone. Then next to that is the experimental hall, where only operating personnel on scientists who are conducting the experiments are allowed, and this followed by offices which is a normal occupancy where people can come and go. So this is in graded manner. How the planning is done is that you can directly not go to the area which is critical. Next page. So Indus 1 and Indus 2, both this zone 1 and zone 2 zoning philosophy is followed. The corridor offices are in zone 1, where the radiation level is restricted to 0.1 milliamp per hour, and zone 2 also is a restricted entry, where the people, operating people, go with the badges, TLD badges. Actually they go with the badges where the radiation is recorded. And zone 3, as is a prohibited area, nobody can go in that area when the machine is on. Next please. That drawing we saw as a whole complex. This shows Indus 1 complex. Here is what you are seeing is hall is 20 meter span with folded plate roof is there, and below that Indus 1 is housed, and there are local shielding. Local shielding is provided all around the ring, and you can see this zone 2, zone 3 and zone 1 are marked as per color. Zone 3 is the area where nobody can go, and zone 2 is the experimental hall. Again, zone 1 is the offices where anybody can go. So actually these shielded area are Here also the wall thickness is 1.5 meter, booster is 1.5 meter. Booster is a very important area where because we see what this type of facility sometimes after some years of operation you need upgradation or you need some component to be changed. So you have to have facility to have some work done here. So actually the part of the wall is constructed as a precast blocks which can be removed. Even the ceiling of the booster area, which is 13 meter by 13 meter, is having a ceiling blocks of 300 mm thick concrete blocks of T shape and Z shape, which can be removed with the help of crane above. And you can just take out your ceiling blocks and you can upgrade the booster area, you can change any component required, and this has been done. So we have to foresee during the planning that we have the facility for upgrading. Because these areas are normally planned in a very compact size. Why? Because these are otherwise it becomes very costly. See, this type of area, because if you increase the area, then the ceiling and wall thickness, everything will go high. So these areas are exactly planned as per the requirement, but should have the facility of upgradation. That is why we use the precast blocks sometimes to provide this. Next, please. Indus 1, then again Indus 2 also, just to give you an idea about that there is a pink color, what you are seeing is a SRS ring, and radiation synchrotron ring is there, and then by the side of lemon color you are seeing the experimental hall, and green what you are seeing is offices. So this is having a beam from transfer line 3, and when it is rotating in the ring, and it gives out radiation which are called synchrotron radiation, and on which the experiments are being done. Inside what you are seeing is the air handling units rooms are there. The control of these rooms are outside. So even in case of operation we don't need to go there. Next please. This gives the photograph, as I said, that how the blocks can be removed from booster hall. So this is a photo of that. Next please. This is the shape of blocks and you can see the photo also, and with the hooks, provision of hook also, that these can be lifted up with the help of crane, and upgradation can be done. Next please. Penetrations are very important. Actually penetration are required. See, if there is a facility, it cannot be just, you have to have a cables, you have to have a air conditioning duct, etc. to be, and at the time of maintenance you need the personal entry also, who can go there and attend. So we have to have in Z shape. Next please. This is a one type of penetration given. See, as I said, that this is also Z, that this is also zigzag, this also is zigzag. But this one is recommended. Why? Because it is seeing two reflections. The incoming radiations is seeing two reflections, and that is why intensity gets down. This is a sliding door which we have seen in some of the sketches, that it has to have. This is a composite lead and steel. Next please. This is a photograph of the same. Next please. This is the view of internal ring. So you can see that this magnet lattice is very stringent, and it requires a special type of foundations also, because these are very sensitive to the vibration and temperature both. So this lattice consists of 16 bending magnets, each of which is weighing 10 metric ton. So we'll have to take care of this and instrumentation for that. Next please. This is actually just a plan showing that we have the offsets in beamline openings also. See, we cannot see, if I want to extrude a beamline, I will have a clean joint. So this is having that. Next please. This is a photograph of the shape. Actually, I have kept the drawing and photograph so that it can be correlated easily. So you can see this is a 400 mm and 300 mm two pipes are having offset in the center, so that it is having no clean joint. Next please. See, at the time of construction, we left the 400 mm and 300 mm pipe as a beamline EP, we call it embedded pipe, and then later on the actual beamline which goes, it has a space around, those are then plugged with lead blocks. Next please. This is a view, actually you have seen that also, that what in the experimental hall the beam line comes, and these beam lines also may have some radiations level. So these hatches are made to protect the outside persons also. These are basically laminate. This is consists of laminates with the lead sheet in between. Thank you. Yeah, any question, please?
Thank you very much, sir. Any questions?
Sir, what's the optimum thickness of concrete to attenuate the radiations?
Yeah, actually, as I mentioned also, this depends on the type and intensity of radiation and the area, because there is a different permissible limits for the area also. So one has to calculate, calculate the thickness required from the provisions. As I said, you have to use I is equal to I0 into mu to the power mu t. Now I is, we know that what is the intensity of radiation we want to limit. It is one, if it is a occupied area, we have to limit to 0.1 milliamp per hour. And I0 is the source which we have to get from the health physics. So there, from the machine sources itself. So that's I0 is known, I is known, mu is the material which you select. So if it is a concrete, then some value is there. If it is a high density concrete, some other value is there. Then the only remaining variable is T, thickness, that you can work out. So it is highly job is project specific. See, if it is one thing, see, you normally visiting a hospital, there you have the X-ray done or CT scans, and then there are some barriers are there. And then people say that you go and only the patient is there, and they also limit the time also. Time of exposure also is limited, so that time also the exposure is to a limit.
Also, you mentioned that you have concrete blocks of T shape and Z shape.
Yes.
Can't we have another type?
Yeah, actually, it depends on the location where you're using. Say, when you are using T shape, basically for wall we are using T shape, because it is forming a T with reverse T, and then with this configuration you make a wall. Okay. Right. So we can use another shape. Only thing is we have to ensure is that joint is staggered. Only thing is we have to stagger the joint.
One more question. I think you mentioned that you import water from Jaipur, isn't it? You import water, something I misunderstood that.
No. Water which you use for concrete is the normal water what we are using for the concrete. It should have the quality of drinking water.
Okay.
Aggregate is right. Actually, aggregate we are not importing from Jaipur, but if it is a heavy density aggregate required, it is available near Jaipur, Jammu district.
Okay.
So if we want heavy density concrete to be made here, we have not so far used a heavy density concrete, because as I said that normal density concrete is preferred as far as space is no concern. If there is no constraint for space, if you can have a larger thickness, we should go for normal density concrete.
Density of lead is very high in comparison to concrete, okay, but still neutrons are blocked by concrete instead of lead.
Yeah, actually, as I said that it depends on type of radiation also. The neutron has the highest cross section, means hydrogen has the highest cross section for attenuation of neutron. Next is boron. So one can use boron also, but this hydrogen is available in the concrete in the form of crystalline water. That is why it is beneficial for attenuation of neutron. Otherwise, we can also use borated concrete also. We can use borated concrete, but it is costly, and then we have to arrange boron also. So these are the some things. And lead also, lead has has got a good radiation property for gamma, but only thing is that this doesn't have the machinability. As I said, it can be cast into the shape, but it is not having a machinability. So if you want to use lead, it has to be used in the block form.
Okay, thank you.
Thank you very much, sir, for your very informative and knowledgeable lecture about various aspects of concrete radioactive shielding material. So it was a great information for all of us. Thank you so much, sir. Okay. Before inviting ma'am on the stage, I have an announcement for the students that we have a quiz after the 15-minute lecture of ma'am, and there is a surprise gifts for you. So please be attentive. Hana? We have a short quiz session for you. Now the next speaker we have among us, Mrs. Gitanjali, a scientific officer at RRCAT. After completing her MSc Honours Physics from Punjab University, Chandigarh, she has done MTech from प.ऊ.व, National Institute, Mumbai in 2015. She was the gold medalist in BSc Honours Physics from Punjab University. She is now pursuing PhD in the field of semiconductor from प.ऊ.व, National Institute. So far, she has been author in 12 international journal and 14 national international conference articles. Her field of interest include third to fifth semiconductor material system and devices. So I invite Mrs. Gitanjali ma'am on the stage.
Hello. Am I audible? So as you all know, we are here to celebrate the 75th Azadi Ka Amrit Mahotsav. So first I would like to congratulate all you. Happy 75th Independence Day. Although it's late, but better late than never. So I am here to give a talk on investigations of optoelectronic properties in 3/5 semiconductor material system. So I just want to say good morning to all. Actually, although it's been 12:30, but you might feel tired and hungry, I think. So have some josh in you. Actually, there will be a quiz after this talk. So all the questions in the quiz that will be covered in all these 3 talks. So if you are giving some answer, then you will get a prize. So be attentive, bear me for maximum 30 minutes. And I have made the PPT in such a way that you can understand. Actually, I made it very easy, so you can appreciate. And if you have any queries, you can ask me after this presentation, or you can even drop an email. These are my email IDs, anytime. So these email IDs I will share on last of my slide also. So I am going to tell about the investigation of optoelectronic properties in 3/5 semiconductor material system. So first, what is semiconductors? You all know what are the semiconductors. So in general, the material system are characterized into 3 categories. One is conductor, then semiconductors and insulators. Here I am showing 2 kinds of bands, red color and blue color. They are referred as conduction and valence band. These are not just 2 boxes as they appear. So basically these are the bands. How they are getting formed, I will explain in the next slide. So it means if there is the charge carriers, that is electrons, which are present inside the valence band that is bound to the atoms, we require some energy to excite them to the conduction band. So basically this valence and conduction band is having an energy gap. So these do not have any state, and this generally referred as a energy band gap. So depending upon the band gap, we can classify them like conductor, semiconductor and insulator. You can see insulator is having a very high energy band gap, more than 5 eV. What does this mean? This means you require some energy to excite the electron from valence band to the conduction band. That energy can be given by temperature, by some light photon or any means. So it means in the insulator you require more energy to excite the electrons. So if the electrons are getting excited to this conduction bands, they will become free and will act as the conduction electrons. So they will participate in the electrical conductivity. So by seeing this, you can very well appreciate, like in insulator, you require more energy. However, in the conductor, they are overlapping bands. So there are many more conduction electrons, that is why they will refer to the good conductor of electricity. If there are good conductor of electricity, in the reverse, as resistivity is opposite to this conductivity, which means that the electric resistivity is lowest in the case of conductors. That means the conductivity is high because we are having freely available electrons. So gold, copper, any other kind of metals like silver, they all comes under the category of this conductors. Silicon. Silicon is a well-known semiconductor, you all know. So it comes in the range in between the gold and the glass. Glass is an insulator. So basically in the semiconductors, they are having a very nice property. Like in semiconductors, if you are providing some charge carriers by providing some doping, you can make them either insulator or conductor. So basically they can cover whole range. And since I am working in semiconductor lab, so I mainly focus only in the semiconductor itself. So in previous slide I have discussed there are two bands which are conduction and valence band. How these bands are getting formed. Semiconductors, as you all aware of the periodic tables, the semiconductor generally lies in this fourth group element. Silicon, germanium are well known semiconductors. So the outermost configuration for these semiconductors are basically having S2 and P2. S2 means they are having 2 electrons, and since this is the S state, means there is 2 electrons in 2 states. However, in P, it can accommodate 6 electrons. However, here we are having 2 electrons in S, 2 electrons in P. So if there is a single atom, only 1 electron, so they will have discrete energy like this. These are the discrete energy levels. When we are considering the case of crystals, when the atoms are start interacting to each other, that means they are seeing some interaction from each other, due to which this discrete energy levels, they are start overlapping to each other. So you can appreciate is if there is a crystal which is having a n number of atoms, they will have initially 2n electrons. I think it's not working. So it's having 2n electron with 6n states in p states. However, 2n electron in 2s states. So when they are start interacting to each other, like nuclei is interacting the electrons of the other, and when they are coming close to each other, there are repulsion forces also with the electrons. So they acquire a minimum position that we refer as atomic spacing. So total we are having 8n state with the 4n electrons. When they are crystal is acquiring the minimum energy state, they will have this 8n state separated into two kinds, 4n and 4n. Since all the charge carrier wants to have a minimum energy, so they all goes towards the valence band and conduction band is free. So we require certain energy to excite the electrons from valence to the conduction bands. So that is why this energy band gap comes in picture, and how we can excite these electrons. So I have already told you that it requires certain kind of energy. So if there are two bands, conduction and valence band, and here I am showing only a 1 electron in a valence band, if you are providing some light photon, photon is a quanta of light, you all know. This photon must have the energy greater than or equal to this difference between these two bands. So when light is shining on it, the electron is transferred from valence to the conduction band. So it creates a vacancy of electrons in the valence band. What does that mean? In semiconductors, we are generally referred to the two kind of charge carriers. One is the electron and other one is the hole. Hole is nothing but absence of electrons. So is this transition will occur or not? That will depend upon the transition rate. Basically, this is the Fermi golden rule which governs this transition probability. Like if the light is shining on it, if it can excite the electron from one state to another state, it will depend upon two parameters. One is matrix element, which tells about what are the selection rules. You all might aware about the selection rules. So depending upon the selection rules, they can give the transition probability from one state to another. And the other is the density of states. So I will explain this density of state more rigorously in my next slide. I can only say that the absorption, if this absorption will occur, it will excite the electron from one band to another. If the transition will occur, that all depends upon these two, mainly on these two parameters, matrix element and the density of state. Here I am giving the absorption coefficient, which is the alpha. This alpha having different natures. Like in semiconductors, we are having two type of semiconductors, direct band gap, indirect band gap semiconductors. All the previous I have shown conduction band, valence band, they are referred to only k equals to 0 value. That means we are not talking about the vector space. We have considered k equals to 0. However, when we talk about the energy band diagram in semiconductors, we usually show their energy dispersion relation, how this energy is getting changed with the momentum space. So depending upon how these bands are getting formed, there can be direct band gap material and indirect band gap semiconductor materials. So the absorption coefficient also varies in these two. Why this vary? Because I already told you that if the transition will occur, it will depend upon the matrix element that will tells if there is some selection rule associated with it or not, and also the density of states that I will explain. However, in the direct band gap material, you can see the lower band is the valence band. The maximum of the valence band and the minimum of the conduction band, they both lie at the same k value. And photon is a quanta of light. Okay, I think you must be feeling sleepy. So photon is having a property like it can only give a vertical transition. So if you want to go from lowest of valence to the maximum of valence to the lowest to conduction, you can very well go with the photon. That is the quanta of light. However, if indirect band gap, the lowest of the conduction band and the maximum of the valence band does not coincide. Like here, it has been seen. Photon can go only up to this. However, in order to go this, it requires some another material. So that to conserve the momentum relations also. So like photon is a quanta of light, there comes a phonon. What does that mean? Phonon is basically a quanta of latest vibration. When we are talking about the crystal structures, the crystal are having some atoms. So when they all vibrate, actually if there is some finite temperature present, they all start vibrating. Due to their vibration, they will give rise to some kind of wave generated. So this wave which has been generated by the latest vibration, the quanta of that is called the phonon. So whenever we have indirect band gap materials, there is photon plus phonon. That is why the absorption is basically consists of phonon that I have marked with the red. So the commonly known semiconductors like silicon and germanium, the mostly you all know like silicon, it is present in all the electronics you are using in your home. So they are generally made up of silicon or germanium. These are two most commonly known semiconductors. These two are having the nature of indirect band gap semiconductors. However, I already told you like in indirect semiconductor material system, there is the involvement of the phonon. So if there is a phonon, there will be some loss associated due to the heat. Due to the temperature, they are giving rise to phonon, and that is why. In my talk, I am basically interested in the optical properties. So optical property means if there is a material and you want to see as the light output, like you can see in LED or this tube light, the light is coming out. So we require that materials in which the losses should be less. So what kind of material we require, direct or indirect? It should be direct band gap. Be attentive, there will be a quiz after this talk. So any optical properties in which we want to see any device, we require direct band gap material system. And in our lab, we are mostly working in a direct band gap material system. So commonly known this fourth group element, silicon, germanium, these you might all know. In our lab, we are basically using 3/5 semiconductor material system. 3/5 means what? You have taken the gallium from the third group element and arsenic from the fifth group. So by combining the two, they again have the same electronic configuration of S2 and P2, because the last valence electrons are only 4. So we are basically dealing with the direct band gap semiconductor material system because their losses are less and we want to make the devices out of it. So I have already talked about this density of state that plays an important role. So what does this density of state means? You might aware you must drive this density of state in your BTech as well as in MSc courses also. It tells about how much electrons are present per unit energy per unit volume. It means if at a particular energy states, if we are having more carriers, it means density of state will be high. What does that mean? If we are having high carriers at a particular state, then it will give rise to more light, or we can collect more electric signal. So it suggests that if we want to make any optoelectronic device, first I will tell you what is optoelectronic device. Opto means optical, means light. Electronic means current. So any device in which light is converted into electric current or current is giving rise to light, that is the optoelectronic device. So first thing we have seen that they should be direct band gap material system in order to reduce down the losses. And the other thing, the density of state should be high, means we will have higher number of carriers for a particular energy states. And these are the different quantum structures. How does this form and how the density of states will get changed, I will explain. First comes the bulk case. Bulk case means if there is a charge carrier of electron and if it can move in all the direction, x direction, y direction, z direction. If in all the direction it is having free to move, then we can say there is no confinement to the charge carriers, they can easily flow in all the 3 directions. That is referred as the bulk semiconductor material system. And if you obtain the density of state, that is the number of states per unit volume by energy, they will show a parabolic relation. It means that there is the E naught after which the density of state will get increased, and below E naught there will be forbidden gap, that is the energy band gap. Now in quantum well, what we are doing? In quantum well, the charge carriers first it was free to move in x, y and z direction. In quantum well, we are basically confining it in one direction. If we are confining it in one direction, we restrict that electron, you should not go to more than this dimension in z. However, you can go x and y anywhere. That is why it is a 2-dimensional. In quantum y, what happens? We are confining it into 2 direction. It is free to move in either x or y. If we are saying it is free to move in x, it is confined in y and z. So that is, it is having a 1-dimensional movement. Quantum dot. Quantum dot, we are confining it in all the direction. So it is having a restricted motion. It cannot go freely in all the directions. So when we are going from bulk to confining it to quantum dot, the density of state is going to increase. So I already told you the density of state should be high if you want to make some device. So it seems like if you want to make some device, what do you require? First is direct band gap material system and other is a quantum dot. It will have high density of state. The energy position are also shifted to high energy and there will be high density. That state will have higher charge carriers. However, when we are making this structure, it is not that easy. If we are looking at these theoretical values like quantum dot will give us a good result, let us make a quantum dot. It's not that easy. There are some growth issues also. So first I am explaining it. It is a technique which is basically we are using in our lab to make such quantum structures. We can make quantum, well, wire, dot, all the kind of structures. This is a photograph of the machine we are having, and the name indicate metal organic vapor phase epitaxy, or you can reverse the words, organometallic vapor phase epitaxy, and it also known as the metallo-organic chemical vapor deposition. So why this different name comes from metallo-organic vapor phase epitaxy? I told you that we are making 3/5 semiconductors, for example gallium arsenide. So if you are making some gallium arsenide, you require some source for the gallium, some source for the arsenic. In general, the third group sources like gallium, aluminium, we are using the organometallic compounds. Like here we are using trimethyl gallium. This is the schematic which shows this is the trimethyl gallium. and we have using this R scene. So both we are basically heating it at a temperature in which they are in the vapor phase. That is why metal organic vapor phase. And what does this epitaxy means? Epitaxy means we have put here a substrate. You can see here picture also. Whatever the substrate we are keeping, all the layers growing on it, it will follow the same crystal structure of this substrate. So all the layers are basically growing layer by layer. So you can say by this manner we can say it is a epitaxial growth technique. Now I am start with very simple of the quantum well. So how we can make the quantum well? In the quantum well there are two requirements. First is the quantum well material should have low band gap than its surrounding barrier layers. If the band gap is less than this, then only electron can go inside it and can get confined. And there is another requirement that the thickness of this quantum well, it should be less than or equal to the de Broglie wavelength. It means we are basically confining the electron motion in such a dimension that it will start showing the discrete energy levels. You can see here there is some discrete energy levels. So in order to make the quantum well, what we require? Two things. First, quantum well band gap should be less than the barrier and thickness should be less than or equal to the de Broglie wavelength. So you all know about this de Broglie wavelength, right? So this is of the order of nanometers, and so you may appreciate this fact. I have shown that transmission electron microscope. It is an experimental data. This tells about the 5 nanometer. So this quantum well is even less than that. So you can see if we are making some quantum well, we are growing the layer even less than that. So by making the quantum well, we are basically growing the layer which is having the thickness less than that. I told you that density of state will be highest for the quantum dot. So why not to go towards quantum dot? Before going to quantum dot, let us see what happens if we are making quantum wells. They are also having some issues with them. So when we are growing these layers, what happens? There is a substrate and the layer grown it is following the same crystal structure. That is why the epitaxy means. So you all know if you want to see some crystal structure, what do? You do the Bragg's condition. 2d sin theta equals to n lambda. At what angle the condition will match, it will give the X-ray diffraction. You all must know if you have course even up to 12th physics. So in our lab we are having high resolution X-ray diffraction. So we are able to, this is a machine, we are able to see what are the barriers and what are the quantum well layers. So depending upon the Bragg's condition satisfy, they will give rise to the crystalline structure. So I have talked about like these are the structure which are grown for the optoelectronic properties. Optoelectronic means optical to light or light to optical, light to current or current to light. First is the photodetector. What does this photodetector do? Photodetector means, as the name implies, photodetector. It should detect the photons. So in this what we are doing, we are shining a light of some photons and it creates the electron hole, and then we are collecting it, it gives rise to this the current. That is what the photocurrent conductor or photodetector do. Basically it is detecting the light. So we have made this kind of detector. It is the quantum well based detectors. So when we have made this quantum well detector, we have used it to even to record the photoluminescence of another sample. That I will explain. But when we have made this detector, we have seen that the quantum well transition that I have shown here, E1 to LH1, E1 to HH1, they are only visible up to high temperature. At low temperature, we are not able to see the signature. Why this happen? So when we are seeing in the another technique, which is basically a luminescence based technique, what does that mean? In the quantum well, when we are shining a light which is having a high energy, it is creating the electron hole pair in the barrier, and every charged particles required to go to the minimum energy. From there they come to the quantum well, and depending upon their radiative lifetime, they will recombine to give another photon. So the emitted photon, red one, is different from the green one in terms of energy. So when we are seeing the photoluminescence, we have seen that if the transition comes only from these two levels of the quantum well, it should be one energy. However, we have seen that we have two transitions. What does that mean? These levels are not flat. They are having some defect associated with it. So if the defects are present and the charge carriers are getting localized, we are not able to get the signal at low temperatures. So it told that even in the quantum well we are seeing such signature, and if we are going towards quantum dot, it will be even more difficult to make the device. So what can we do? Quantum dot is difficult in terms of growth, but we can apply the magnetic field. What does this magnetic field do? Magnetic field simply what do? When you are applying the magnetic field, according to Lorentz force, it confines this. Basically, the force is given by force equals to q.v.b equals to mv square by r, which means if you are applying the magnetic field, the radius is getting close by. So if we are applying the magnetic field to the quantum well itself, in quantum well we have already confined it in the z direction. Means it's 2D dimensional structure. The electron can go in x and y, but it is confined in the z direction. But if we are applying the magnetic field in the z direction, it will confine it in x and y also. Quantum well will become the quantum dot, 2D to 0D. So by applying the magnetic field, we can make quantum well to quantum dot. So it's an additional feature. So when we are applying the magnetic field, the radius is getting close by, so there will be more recombination, and density of state is also going to increase. I already told you the density of state will be maximum for quantum dot and minimum for bulk. So that is also increases. All will this increase the photoluminescence signal. So this type of confinement, when we are having one dimensional by z and x and y by magnetic field, it creates another kind of states that are the Landau levels. So in order to, this is the setup which we are using in our RRCAT. You can visit at any time. So here this is a superconducting magnet in which we are placed some sample. The sample is placed at around 1 to 4 Kelvin. So you can appreciate the fact that 1 Kelvin is in degrees Celsius, right? So basically when the laser is being reflected by a small mirror and it's been put inside the optical fiber. This is the schematic. From there we can see what is the effect of the magnetic field. Usually you do MRI, you can have the magnetic field up to the range of 1, 1.2, 1.5 Tesla. Here we can achieve magnetic field up to 8 Tesla. So when we are applying the magnetic field, discrete energy levels due to all type of confinement, these are known as the Landau levels. And from their behavior we can estimate various material parameters like mass and binding energy, etc. Apart from this, our group is also making some DBR structure, that is high reflected distributed Bragg reflector. Already Pankaj sir told you about the LIGO project. These mirrors we have sent to them to characterize them also. Actually they are using oxide mirrors, and in replacement of that, these are the monocrystalline crystal which are having low loss, so they are looking for them. So this is a very good system. You can appreciate it. This is the system. When we are growing any structure, we want to make some device. You are saying we have made some detector, but growing only doesn't make a detector. You have to take a contact. So in order to make a contact, you require some lithography. What does this lithography means? You all must use some chewing gum in your childhood, and there comes a sticker in which you imprint whatever the sticker comes, it comes on your palm, right? Here what we are doing, we are putting some mask and photoresist. So by putting the light, we have imprint whatever you require to put on this sample, you can coat very well. So initially we were using the system of mask based, in which UV light is coming and we are using conventional mask to imprint whatever the projection. This is the system, very economical. It's around 1.5 lakh, and you can make this system very well in your lab also. The same projector which you are seeing, this is giving some light, you are seeing some talk. Same projector, BenQ projector, is used to make this maskless lithography system. What does this mean, maskless lithography system? Lithography, I told you that you have making some structure you want to put it on the sample. So whatever I am writing on the PPT, you are looking here. So if I want to change, I will write it down in the computer and it will show here. Back. So in the same case here, whatever the mask you required, you just design on the computer this projector, which here it is giving like this. However, instead of giving like this, we have used some microscope, which is instead of this, it is focusing it onto the sample. So projector is giving us two components. One, it is having a UV light, which we can, by using this, we can develop the samples, and other, it is very easy. If you want to write your name, you just come to our lab, we will write and you will get your name on the sample within 5 minutes. So it is that easy. So we are using this kind of system, which we have indigenously developed to make several kind of devices. I have told you 2 type of devices. First, current to light, means you are giving some current, electric current you are giving, and in the output you are giving, you are getting some light. What are the example? Tube lights, you are seeing some light is coming. Lasers, LEDs, you are giving some electron hole pairs, they are recombining, they are giving rise to the light. These are the semiconductor laser, you can see these are the semiconductor lasers. These have been developed in our lab by using that indigenously developed master lithography system. Apart from this, other way around, light is falling on it and you are getting the electron hole pairs that give rise to the photodetector principle. So different type of detectors we have made in our lab, depending upon the user requirement also. We have given different type of detectors in different areas. Like in our RR-CAT, there is a high power circulator. So in the high power circulator, when the high power is circulating, sometimes arcing occur. So if the arcing occur, it can damage this RF power supply. So what they have do, we have made the detector depending upon their requirement, and since it is having the spectra in this range, whenever the spark comes, it will act as a safety measure. It will switch off the system. So it acts as a safety measurement. Apart from this, we have made a dual element based detectors. There is some kind of spectroscopic lab in which they require to see the voltage change. If they are not commercially available, 2 different detectors, if you are seeing to see what is the voltage difference, then they must be identical. So it is best to make a 2 detector only single chip. That is what we have done in the dual element based photodetector unit. And Parchani sir and Pankaj Mishra sir told you about X-ray, gamma rays, that are the high energy rays. And they have been used to irradiating foods also, and many applications. So the detectors which we have made, they have the capacity to detect that high energy photon also. In the previous slide, I was restricted up to the visible light only. However, we have made the detector using that system, massless system, and we have checked different materials. These are the different materials, and depending upon their characteristics, X-ray energy range, we are detecting different materials. So they are having the application even in the extreme range of X-ray and gamma ray. In the gamma ray, what we have done, we have put some material which is having a scintillator, cesium iodide, thallium doped. So when the gamma ray is falling on it, it is converting high energy gamma to the photon, which is having the spectra at around 500. This is well matching with the spectra of our detector. So we are able to detect that gamma ray photons also. So all these are the applications which we have did with our lab, and I want to acknowledge my lab members, Dr. V.K. Dixit, Dr. T.K. Sharma, Jay Prakash, Shailesh Khamari, Ravi sir, Abhishek sir, Payal, Taya, S. Porwal, maybe you can read that. And thank you. Thank you for your kind attention. If you have any question, you can ask me now. And even if you want to inquire anything later also, you can drop email to this email IDs. And we are having a quiz after this. I already told you, so be attentive.
Thank you, ma'am. Any questions? No. Thank you, ma'am, for your excellent lecture.
So if there is no question, that means either you are not able to get anything or you are get everything.
All the things.
That quiz will tell.
Thank you so much, ma'am, for your excellent lecture on semiconductors and their applications. Thank you so very much. Now, to continue with the quiz, I request Dr. Ajim Shah and Shri Patidar to please come on the stage. So everybody is ready for the quiz? आवाज ही नहीं आ रही है कि नहीं है?
Even if you are giving some wrong answer, it's okay.
So shall we start the quiz? Okay.
Hello. So, are you ready for the quiz? Okay. So, we have a few questions. Those who are giving the exact answer, we will be giving a surprise gift. Our research scholar, Parsarthi, will be engaged in that. Okay? First question will be, please listen carefully. If you want, I will repeat once again. In the following electricity generation plants, which one requires smallest land acquisition? First one, hydel. Second one, nuclear. Third one, coal. These are the options. First, okay, you are the first person. Okay. Okay, right answer. You can. Okay, everyone want me to be here. Since my height is enough, that's why I stand there. Okay. Okay, done. Next is, how many nuclear reactors are working in India? How many nuclear reactors are working in India? We have three options. First is 22, second is 30, and third is 15. Okay, here. Okay, okay. Very good. Next is, how much is the capacity of all 22 nuclear reactors together in India for electricity production? Here also we have three options. One is 1000 megawatt, second is 6700 megawatt, third is 3000 megawatt.
One can be raised.
Very good. Anyway, Anjali is telling the right person. So, here, idhar. Okay. Now comes the next one. We have mentioned in the presentation regarding the indigenous fabrication of a machine named Babatron II. Do you remember what is the exact use of this machine? Options are treatment of osteoporosis, cardiac related treatments, cancer treatment.
One. Raise your hands, don't give the answer. Raise your hands, we'll come to you. The boy. Don't disclose answers, just raise your hands, they'll come to you.
Now comes the next. It is already related to same machine. In the Babatron II, which isotope is used? Options are cobalt 60, uranium, and U. Okay, sorry. Okay. No. Finish nahi.
दिया क्या उधर?
Okay. Continuing. What is the full form of BRIT? BRIT. BRIT. It was in presentation. BRIT. Don't go to the internet. I am seeing someone going to the Google.
We can
So,
skip question.
I will give you, if you don't remember, can you at least say in which technology the BRIT is related? Okay, very good answer.
Very good.
Now, comes a simple question. So, what was the old name of Raja Ramanna Center for Advanced Technology?
That girl. Partha?
Okay.
Yes.
Okay. Now, which is a type of radiation source used in Indus 1 and Indus 2? We have three options here also. Accelerator, laser and nuclear.
Just raise your hand. Partha, go ahead.
Okay,
He's
right
saying
answer.
accelerator and he is saying laser. Partha.
Now comes to a R&D device we have devised in our center named Neil First Me. A device was recently fabricated in RRCAT for healthcare application. Can you just tell which is a virus could be inactivated using this device?
Partha, go there.
Options I have. Should I give option? COVID. COVID है ना? No. Neil was me.
उनको पीछे को लटके इनको मिल गया ना?
COVID.
You already got ना?
Okay, that is the judgment. Correct. Now the last question from my part. There was one Yendra named Seedar Vaha Yendra. It's a new technology developed for the transportation of cold cargo. Can you say which is used for refrigeration which is a refrigerant actually is used for refrigeration?
Answer? Yes.
This is second answer? Yes. Okay, right. I can now hand over to.
Hello everyone, myself Alarak Patidar. My questions are quite easy, but I don't have options. But questions are easy, okay? So first question is, an alpha particle consists of how many protons and neutrons? An alpha particle consists of how many protons and neutrons?
Yes.
And neutrons? It's answer is
You
very.
can give her. Actually, she
Yeah.
has given half of the answer.
Yeah. So the answer is 2 proton and 2 neutrons. So she has given a answer, but which is half correct. Only 2 protons. So 2 proton, 2 neutrons. Okay. Okay. Pardon then.
That's why we have given you the pen.
Congratulations. The next is, which type of radiation travel fastest in air? Very good, very good. Gamma radiation. So out of alpha, beta and gamma that we have discussed, gamma travels fastest in air.
If any other knows, then they can also get a prize. Actually, only one person is getting prize. It's not a good thing.
Okay. The next question is, best shielding material for gamma radiation. We have discussed.
Yes.
Yeah, please.
Yes.
No.
But did you say?
That is the wrong answer. Yes. Yeah, lead. Lead is the correct one.
Wait, you teased out.
I think it is your third answer, correct. Third correct answer. Yeah. So she has got 3 prizes.
You can share your pen with your friends.
You should be very aware now, you know. Anyone can take your pen. Which is the best shielding material for neutrons and gamma radiation in common use? Anyone on this side? Or only
That
these two
side.
girls are giving the answer all the time?
That guy.
Yeah. Who is? Yes, please. Yeah, concrete is the right answer. So when it comes to shielding both neutrons and gamma, we require a hydrous element and then thickness also. So concrete is the right answer.
गलत आंसर कोई वो नहीं है बहुत अच्छी है कि आप
At least you can try.
Yes, at
That
least
is
you can try and
the purpose of this interactive session.
You have this confidence that you can give some answer. Even it is wrong, then it never mind.
Okay, this one is a little bit tricky. So if we will, what will be the exposure rate if we triple the distance from the source? If I am going to triple the distance from the source, what will be the exposure rate?
No answer. So
Yes, please. 1? Please pardon?
1.8.
We are tripling the distance, yeah. Now, closer. Yes, please.
That person.
1 by 10. No, that is closer but not the right answer. 1 by 9 is the right answer. So, in the second presentation, sir has discussed this exposure rate constant thing, that I multiplied with the distance square is constant. So, if you are tripling the distance, then the exposure rate will be 1 by 9th. Okay. The next question is, why concrete is good for neutron attenuation? Yeah, great. Very good, very good. That is the right answer. You can clap, at least he is trying and she is given right answer. Please. Another one is, which concrete will have less thickness? Your options are heavy density or the ordinary density concrete. Less thickness for shielding. Yeah, good. High density concrete. Please. My last question is, in the second presentation we have discussed why Z type of entry is provided in radiation shielding area. Why Z type of entry is provided? Yes, please. No. Yeah, right answer. So what we are trying? We are trying maximum number of reflections of the beam so that the intensity can get reduced. Yeah. This is from my side.
So only 6 questions are left for me.
6 questions are left for the ma'am.
Last
Hello?
questions.
7.
So buck up, guys.
I would like if the person who is not giving the answer before, that can participate. Even if it is wrong, then it's okay. So, very simple question to start with. Which material will have higher conductivity? Conductor, semiconductor or insulator? Don't give answer like this.
Everybody knows.
Don't give answer like this.
Actually, I was checking that you all are attentive or not. So this was
Actually, I just gave a question that you may find interesting, and even the person who are not participating, that can participate. So, which material system will have high density of states? Bulk, quantum well, quantum wire, quantum dot. Why are you all giving the answer?
Don't say answer. Just raise your hands.
No one will get the pen. Either my questions are very simple or I have explained very well.
Previously said they have understood all the things.
What does this quanta of lattice vibration known as? That, huh? Yes. Partha? Name any semiconductor material system. Just raise your hands. Any semiconductor material system. Just raise your hand. Huh? Gallium. Gallium is not a semiconductor, it's a... Wait. So I have to reframe the question again then. What type of semiconductor silicon is? Just raise your hand. Direct or indirect? Indirect. On what phenomena this laser LED works? Light to electricity or electricity to light? Just raise your hand. Just raise your hand. Light to electricity for what? Laser or detector? Light to electricity. In laser, you are what you are saying? What is the output? That is the light. So there is no option to go to other. Actually, there is only 2 options. What will happen to the density of states if we are applying the magnetic field? Will it increase or decrease? Just raise your hands. That. Actually, I am giving opportunity to all those who have not covered. How much pen we have left? 4. So very simple question. So you all can raise your hands. Which material will have highest energy band gap? Conductor, semiconductor, or insulator? Just raise your hand. Just raise your hand. For that. I have framed very simple question. So if we want to make some device, like I have told you about optoelectronic device, what kind of material we require? Direct band gap, indirect band gap, and what type of quantum structure? Just raise your hands. Direct band gap or indirect band gap? Direct band gap. And what kind of structure? Bulk, quantum dot, quantum bar, quantum dot. What kind of structure you require? Yeah, quantum dot. Density of state will be higher. Again, one very simple question. I think you all should raise your hands now. What is the quanta of light called? Raise your hands. Who have not got this prize? Patra. How many pens we have? Only one.
Only last question.
So should I throw some difficult question or simple one? Difficult? Okay. That I should frame actually. Actually, all these are having very simple questions. So let me give some simple question itself. So one difficult question, okay? So what do you think when we are increasing the temperature, what should happen to the energy band gap? Either it should increase or decrease. What you are thinking from your logical point of view. You have to give the answer and explain it also. Just raise your hand if you have the answer why it is so. It is not true or false. That girl. It should? If we are increasing the temperature, the band gap should decrease? Yes. Why? I already told you, yet you have to give the answer. It's not like increase or decrease. Anyone? So one is saying it should decrease and one saying it is increase. It should decrease, that is true, but not due to the vibration. Yeah, kind of. You can analog that. So you may share the pen. Thank you.
Thank you so much for such a wonderful and excellent quiz. I hope all of you enjoy the quiz. Yes or no? Then appreciate them. Give them a round applause. Thank you so much. Now I request Dr. Pankaj Mishra sir and Shri Govind Panchar sir to come on the stage to felicitate the Principal IPS Academy with the memento. As the Principal ma'am, Dr. Prem Gupta ma'am is on leave, so I request Dr. Pradeep Joshi, HOD Department of Mathematics, to please accept the memento. Please, sir. Sir, please on the stage. Thank you so much, all of you. It was a pleasure to have all the dignitaries with us and for such a wonderful lectures. Now, I request Dr. Javeer Singh to propose the vote of thanks.
Thank you, Rana ma'am. It gives me an immense pleasure to deliver the vote of thanks for this event. All dignitaries assembled here, I would like to thanks to our guest from RRCAT, Dr. Pankaj Mishra sir, SOG RRCAT, Dr. Panchani sir and their teams. I would like to thank our principal ma'am and Dr. Pradeep Doshi sir for their support and valuable suggestions. I would like to thank our HODs from different department, Dr. Jitendra Pati sir, HOD Physics, Dr. Ruchi Srivastava ma'am, HOD Chemistry, Dr. Deepali Shukla ma'am, HOD Biotechnology, and many other faculties of our ISR. I also thankful to say Dr. Sandeep Gupta sir and his team for their support for this event, and I am very thankful to our coordinators, Dr. Amit Thakur sir and Rana Jadam madam for their support, and I must say thankful to our students for their participation in this event. Thank you, Sanjay.
Thank you, Jaiveer sir. Thank you all of you for such a wonderful program. I'm once again thankful for all the delegates from RRCAT, HODs, and all the students to hear us with patience. So thank you so much. Thank you.